All right. Hello, everyone. My name is Wahida Akberzi. My colleague's name is Jeffrey Johnson, and we represent CSUN Smart Prosthetics, where we developed an affordable, lightweight, and transradial prosthetic arm with multiple capabilities. Now, there we go. We are a team of 10 people who, throughout the 2020-21 cohort, we did our project at the height of the pandemic, so we didn't have as many resources as other previous cohorts, but we were still able to achieve what we wanted to do for the year. Now, as an introduction to the topic of prosthetics, there are 3 million people in the entire world that face some kind of upper limb loss. And upper limb loss can affect one's abilities to do daily tasks that we all take for granted, such as picking up common items or nonverbal communication. Companies have taken the initiative to create prosthetic arms in order to mitigate that issue. But our team concluded that the arms in the market right now can be inaccessible due to their really high price point. This is where we poured all of our research into several prosthetic arm technologies. The DECA arm was the first arm we looked into. It was published in the Journal of Prosthetics and Orthotics International, and it featured both a foot controller and compound wrist movement. Unfortunately, affordability was not investigated, and our team valued affordability. This is where we researched the cyborg beast. This study was published in BMC Research Notes, and it only cost around $50. Most, if not all, of the hand was also 3D printed. One big limitation, though, was that it had limited movement because it was a purely mechanical arm, and we wanted our arm to do more than just open and close its hand. That was all it could do. Based on the research of our previous cohorts on MataPro 1 and MataPro 2, the fingers were actuated based on shape memory alloy wires. And based on the research for MataPro 1, the thermal conditions actually melted the 3D printed parts. So MataPro 2 refined the design by adding a carbon fiber skin as well as a cooling system. Both of their research was actually successfully published into journals, and we plan on pursuing our research, and we plan on placing our research in a journal and have it published. One of our last arms is the My Own project, which is the last arm we were inspired by. It could be able to successfully pick up items using the myoelectric control system, but the limitations that it had was that there was no haptic feedback system, there's no wrist rotation, and the myoelectric control system had more limitations than initially thought. The main limitation for myoelectric sensors was that there was muscle fatigue because the muscles are interlaced and it made hard to interpret signals, and one or two muscle groups were being constantly activated, which just gave the user pain. We've considered voice activation, but not everyone is comfortable talking to the prosthetic arm at all times in all environments. And we've considered brainwaves, but the concentration needed to use brainwaves was too much to the point where it would render the arm unusable. And our main problem was that functional robotic arms that are in the market are expensive. So we're trying to create an arm that is not only had multiple functionalities, but was also cost effective and lightweight. And this is where our design objectives come into play. So we wanted to create a foot control system where the components of the foot control system would communicate to the arm wirelessly to control the arm. There would be a mechanism to rotate the wrist, and haptic feedback would also be implemented so that the users can have a sense of touch. This is how our team was split up. We have our team of wrist rotation, which was responsible for designing the wrist rotation mechanism. We have tactile feedback, which was responsible for making the haptic feedback capabilities of the arm. And the foot controls team was responsible for designing both the controls as well as the overall design of the foot controller. We have 4 milestones that we went through throughout the entire year, where we did a PDR around December 2nd. We did the CSUNposium presentation around last month. This senior design project showcase was also a milestone. And at the end of the semester, we are going to complete a research paper and submit it to a journal so that it can be published. In order to achieve those milestones, our Gantt chart showcases all of the tasks we needed to do in order to complete both the milestones as well as the project itself. Right now, it only displays several weeks, but the entire Gantt chart shows the entire schedule when you change the display week. For the standard development process model, we had essentially a metaphorical staircase where we started at the top with research and discussion of ideas and decision for parts and so on and so forth. But in case something went wrong, or in case we wanted to improve on the mechanisms, we would go back, do some more research, maybe testing, and completely iterate on the process until we refine our design.
All right, so here we're looking at the full assembly of our 2021 Smart Prosthetic Transradial Prosthesis. The arm is comprised of a palm, 5 fingers, and the forearm. The forearm houses much of the system assembly, including the smart servo motors. Those will be controlling the activation in the fingers, as well as an inner shell design, which will allow for the wrist rotation. Specifically on the palm itself has a curved shape, better for picking up rounded objects. The fingers are made up of a 2-joint mechanism and a slight curvature in the top portion of the finger to allow for a better grip structure. They are held together with an X-frame finger mount. These are easy to assemble and print. And then on the back side of the fingers, we have a removable access nail. This will allow us to thread and wire the things that we need to actuate each of the fingers. So we ran threaded fishing line from the smart servo motors in the forearm up through the fingers and then back down to the servo motors to actuate each of the fingers. And then we have elastic bands sitting on the back side of the fingers to retract the fingers after an activation. Also, each of the fingertips will have a pressure sensor built in, and I'll talk more about that in haptic feedback. Here we have the forearm design. This is where we've mounted much of the assembly, including the smart servo motors made by Herculex. These motors were chosen because of their reliable accuracy and their strength. At 7.4 volts, we can obtain about 10 pounds force per inch. We have 4 of them to actuate each of the fingers. One motor will be there to actuate both the pinky and the ring finger, while each of the other motors will have their own individual finger. We tied this into the Arduino Nano. We chose the Arduino Nano because of its size and familiar programming. It also comes with a lot of reliable parts and libraries, so it was easy to work with. It's powered by a 7.4 volt LiPo battery. This is essentially just an RC car battery. It's easy to find and purchase, so it's simple to replace. We have a 5th servo motor in the back of the arm to rotate the shells around each other. It does that using the rotational gear. It has a normal gear and an inverted gear mounted to the outer shell, which will allow for rotation. Just a quick note, the battery can power the arm for about 30 minutes. So here we have some visualization of the arm rotation and the assembly. All of the components will be rotating together inside the arm to alleviate constraint or entanglement. And then the outer shell will be mounted to the residual limb and will be stationary. Also mounted to the residual limb, we have the haptic feedback system. This is a system that will allow users touch sensation when utilizing the arm. This is beneficial for performing actions without looking or just unable to see, as well as just a quality of life improvement for amputees. We have also been able to utilize the sensors in the fingertips to adjust control in the finger activation to prevent too little or too much movement with the finger activation. Here we just have a quick video. It's a little quiet, so you might have to turn up your sound of just the sound from the vibration motors when they're activated through the pressure sensors. All right, and here we have the foot controller. The foot controller is a simple lightweight design that will mount to the top of the user's shoelaces, as well as 3 buttons that will sit inside the user's shoe. The system is comprised of another Arduino Nano and an IMU, a transmitter, and a 9-volt battery. The transmitter is used to send a wireless signal to the prosthesis for controls. The IMU is a gyroscope sensor that will measure position and tilt, and that combined with the 3 buttons, we can perform programmable gestures for the arm. Here are some of the most widely used gestures on the market. We more or less just followed their lead and tried to perform gestures similar to what other marketed arms performed. This is our testing arm, just performing just going through all of the gestures. So for testing, it has been pretty troublesome. We've had quite a bit of setbacks with so many little parts tied in to such a small chassis. We're just bound to have problems. So here we have a couple videos of the strength testing apparatus. Here we use a dynamometer to test the strength. It is measuring in newtons currently. So I'll go ahead and play that video. So in this video, the middle finger is refusing to activate. So we get around 20 newtons. Once I was able to get the middle finger to activate, we achieved around 30 newtons. However, it had a failure right afterward. So this joint here at the wrist actually snapped, and we had to 3D print a new joint. This was probably due to just not having the full arm assembled together for this kind of testing. So for manufacturing, we used as many 3D printers that we could get our hands on. It was very scarce to print parts due to the COVID-19 pandemic. So we printed as many parts that we could in whatever materials that were available. Towards the end, we were left with the parts that we liked. Overall, these are the 3 materials that we printed with. We had resin, ABS, and PLA. The parts that we really liked for the arm were the ABS and PLA. So our total budget for this project was $1,700, and we were able to build an arm that cost $460, which compared to the most comparable arm on the market, that one will cost $3,000. So we're well under the line for the market. In conclusion, the 2021 Smart Prosthetics has created a transradial prosthesis that features haptic feedback, wrist rotation, and is controlled using the foot. Thank you.
I have a question. So one of the goals was to be cost effective, which you demonstrated from a parts standpoint and a manufacturing standpoint, but there's a lot more that goes into making a prosthetic available for everyday patients. So there's a lot of regulatory and compliance that gets added on. And working at Medtronic, I see that every day. So the real cost is missing, some of that components, which is probably why the competitor costs $3,000. There might be $1,000 more in compliance and regulatory and some of the other things in running a business. So that's just some feedback. My question is, what feedback have you gotten from actual patients, or do you have access to have somebody that is under this condition actually test out the arm?
We don't necessarily need an amputee to test out what we're researching. The closest thing that we have is a research that our previous cohorts have done. They have asked amputees, did a survey with amputees asking them what they would like about arms. They mostly stated some sensory, which is what we've incorporated with haptic feedback, and the price point. But beyond that, this was mainly just to have wrist rotation, foot controls, and the feedback system implemented.
Yeah, to add on to that, this was mainly a research-based project. Compliance and all of those other factors would account, yeah, but for this was mostly as like this was mostly a proof of concept project.
Okay. I've seen this project evolve over the years, and it's advanced, and I just started to wonder, is it meeting the needs of an amputee? What feedback would they have that would require a redesign, or what new challenges would they have or adapting to this? And obviously, this is a senior design project, but maybe something as feedback for the next year's project as part of the evolution of this project.
Yes, that is something that we should look into. Yeah.
So I had a couple questions. Did you have any quantitative criteria? Like, were you looking for a specific grip strength? Were you looking for specific ranges of motions? Things like that?
Our specific objective is to mostly have it rotate its wrist and do the 5 gestures we mainly wanted.
So I think our quantitative values would be human values, and we have, I think, 310 degrees of wrist rotation, which is pretty close to what a human can do, maybe a little bit more. And then for the grip strength, a typical human averaged about 350 newtons of grip strength versus our 30 newtons. So we're well off the mark. But the servo motors that we found are currently the strongest that we could find on the market for their size, and still be able to build the forearm around them. So currently we're investigating ways into improving the grip strength, but the wrist rotation is more or less right where we want it.
Right. So unfortunately, we are out of time for questions. So we're almost here for the next presentation. So I mean, you can always email or send the questions directly to the team and the advisor, and I'm pretty sure they will be glad to answer all the questions you have. So I would like to thank the Smart Prosthetics team